I want to begin by thanking my lab for, basically everything that I'm going to tell you about today is stuff that we've been thinking about and working on over the last, I guess, almost 7 years now at Berkeley. And of course, this would not be possible also without collaborators who've come alongside us in discussions and then also funding agencies that have really allowed this work to take place. Okay, so I want to begin with a little bit of more of quantum. I hope you're not bored by that term, but thinking in terms of sort of what I would say are maybe the two quantum revolutions that we've had so far. So the first quantum revolution was at the turn of the 20th century. In the early 19th century, it had been shown in Thomas Young's experiment that you could diffract light, right? And so light was accepted at that point to have wave-like properties. It wasn't until this experiment by Davison and Germer that they showed that yes, electrons also have this sort of wave-like nature. And so then that was actually towards the end of what I would call the first quantum revolution, with sort of the development of a number of equations and models that now we sort of come to expect. And then in chemistry, and physical chemistry and physics, this sort of culminated in what's known as the Schrödinger equation, right? And so this was sort of the first quantum revolution where I think we started to understand this wave-particle duality of matter in general and in particular of electrons. And then I think that the second quantum revolution, which we're in now, is really thinking about how do you engineer and manipulate those properties towards various applications. And we just heard a beautiful summary of some of those sort of forays, and in various areas. So we heard about quantum computing and simulation sensing, and even you mentioned cryptography. So what I would like to talk about are this sort of smaller subset, this last subset here of quantum materials, right? So we heard about defects, we heard about even superconductivity. The systems that allow these phenomena to exist are what we call quantum materials. And I think of them as the things that allow you to sort of see and touch quantum in a way, right? So it's interesting, we had a couple of nice talks about sort of galaxies and stars, right? Very big, and right now we're focusing on, when you think of quantum, you think of something very, very small, right? But quantum materials, and when I think of quantum, the second quantum revolution, is really quantum mechanics that you can see and touch, right? It's quantum mechanics you can use and literally leverage to levitate a train, right, on some tracks. It's also, as somebody who's a chemist and comes from a background of electrochemistry, electrocatalysis, I think of it as related to, okay, how do we rearrange bonds and molecules, right, for some maybe energy conversion or storage process, right? So quantum really coming to the macro scale, that's what the second quantum revolution is really about. And when we think then about quantum materials, I want to give you an example of one thing that still kind of blows my mind when I think about it. So if we think about, right, electrons have this particle and wave duality, right? But electrons have a mass. They're really, really light. That's their mass. But it turns out that if you have electrons in different crystals, you can basically make them behave as if they have very, very different masses. So for example, electrons in graphene, I'll talk more about graphene later, but electrons in graphene, which is this honeycomb of carbon atoms, so you just have carbon atoms in a honeycomb structure, electrons in graphene behave as if they have no mass, right? In that sense, they behave like photons, which is really, really interesting, right? Irrespective of their energy, they move at the same speed, right? But then you put them in a different material, this material over here, and they end up having masses that are 10, in some cases 100 times the mass of the free electron, right? This ability of sort of you to make a material, make a crystal that can totally radically alter the way electrons behave, that is what lies at the heart of quantum materials. And sometimes it is the interactions between different electrons, like we heard about, or sometimes the interaction of the electrons with the vibrations of the system, or with light, and so on. Okay. And so the power of quantum materials really lies in our ability to tune what those crystals are made of, right? By taking atoms from the 118 elements of the periodic table, controlling how we configure those atoms into crystals, or maybe not crystals, right? They could be very disordered, amorphous structures in various ways. And then even control how big is that crystal, right? Is it really, really thin, a single layer or a few layers, or does it go on effectively forever from the point of view of the electron? Okay, and so when we think about the last several years or decades of sort of people's work in the area of quantum materials, the process of sort of trying to understand these phenomena and new discoveries has been driven by, well, you know, and this is maybe 30, 40 years ago, the idea was, well, if we can grow, you know, really nice crystals of something that we're targeting, then we can, you know, achieve some or observe some phenomenon that is maybe very, very fragile, right? We want to make crystals as clean as possible. And so we're going to find ways of growing large crystals, and then we're going to do a lot of structural experiments, like this is an electron microscopy image, so each of these bright dots is an atom, and we're going to make sure that all the atoms are in the right place, right, in this bulk crystal. But along the way, also then has sort of been the realization and development in how we make those crystals, right? So for example, there are techniques of thin film growth. So instead of trying to grow a bulk crystal, well, maybe we can grow these as layers on a substrate, right, on a surface, where you know, and then we discover things like, oh, if we can layer two oxides to, this is lanthanum, aluminate, strontium, titanate. They're both insulators. They don't conduct electricity. But we can layer them on top of each other, and somehow at their interface is a metal, right? At the interface, you can conduct electricity, even though they are insulators themselves, right? And in fact, under some conditions, they will superconduct, which I'll talk about. Other related phenomena is like the quantum spin Hall effect, where you have some material, again, in a layered configuration, and electrons with different spins. I'll talk about electron spins in a little bit, move in different directions in the material, right? All these kinds of interesting behaviors which lend themselves ultimately to technology, right, in one way or another. And then, you know, you can even have the same material, but if you make it at different sizes, right, of crystals. These are diameters of the crystal. They're like little spheres, 2 nanometers, 2.5 nanometers, 3.94 nanometers. They have different colors, right? These are used in some TVs, right, to create very, very bright, fine, sharp light sources. And this led to the Nobel Prize not too long ago. Okay, and so along the line of sort of new materials, new methods that have enabled new discoveries, two-dimensional materials have, in the last about 10 years, 20 years, really come onto the scene in a big way. And so these are solids, crystals that have, you know, strong bonds within the layers, and the layers can have different structures. But then out of the plane, you can see that there's some gaps here. They're sort of loosely stacked, very weakly stacked, and then you can sort of mix and match them in various ways, right? And then you end up with emergent properties, new behaviors that you know, are not found in any of the constituent layers themselves. Likewise, there have been new tools that have been developed, right, for understanding and visualizing these materials. Electron microscopy has allowed us to see atoms with greater and greater clarity, and we've even found ways of, in the electron microscopes, this is some of our own work, being able to identify what local domains are doing, right? These are ferroelectric domains, right, where there's some local polarization, local dipole that is oriented in one direction or another, and you can image those in real time. So operando, people, you know, this is some work from Berkeley, finding ways not just of imaging atoms, but imaging bonds in nanoribbons. Doing experiments where you can look at very, very fast timescales, you know, of picoseconds or attoseconds, trying to figure out what is going on in a crystal at some of the, you know, fastest times, right? These have all allowed us to probe and understand these systems. And in even, you know, maybe the frontier of this field is sort of saying, well, instead of relying on equilibrium or the most stable way that we can arrange atoms, can we find ways of making crystals where they're in a really unstable configuration, right? And then we'll get new properties. Or instead of thinking about crystals in space, right, of how the atoms are configured in space, can we think of time crystals where we introduce some periodic driver, like a light source, right, where it's periodic in time, and then that reconfigures the way the electrons behave, because they don't only just see the periodicity in X, Y, and Z, they now see a periodicity in time, right, of some source. So these are some of the directions. And I think that to sort of give you an idea of why this is all important, well, one, fundamentally it tells us about our world, but also it holds the key to more efficient communication technologies, new opportunities for communication. I look to this trend over here where I see that 90% of the world's data being created in the last 2 years really sort of makes you scratch your head and realize how explosively, right, we're producing data, and that has an energy cost to it. Every time we send an email, every time we run some operation, it has to go to a data center, and there's a large energy cost, and this is going to become even more and more severe with our race towards to embrace artificial intelligence, and of course. So now we're starting to realize that, wow, these things cost a lot of energy. Okay, and likewise, what we need to understand is that controlling these materials' properties is also critical for harvesting energy from other renewable sources like the sun and so on. So you put up, I thought I had 25 minutes. Yes, okay, I saw 5 minutes up, so I was worried that, okay, I'm good, all right. So, I want to talk about 3 works from my group today, with this as sort of the context and the backdrop. I want to tell you about some of our work to look at the structure of a superconductor, a 2-dimensional superconductor. I want to also tell you about how actually the same material has allowed us to look at new chemistry at surfaces. And then lastly, I would like to talk to you about new magnetic materials for so-called spintronics, all right? So 3 vignettes of our work, okay? So when I think superconductivity is maybe one of the most sort of canonical sort of quantum phenomena. It's the one that, when somebody claims that there's a new room temperature superconductor, it gets a lot of interest, whether justified or not. But this idea that electrons interacting with each other and with their crystal can, expel a magnetic field, and so something can levitate, and you can flow electricity through this substance without any resistance. It's sort of really, really fascinating, right? And usually, superconductivity requires you to have large densities of electrons, and you need to be at very, very low temperatures. That is sort of conventional superconductivity. And there's a very good reason for that related to the mechanism of that superconductivity, which we understand, right? That conventional superconductivity, we understand, is mediated by lattice vibrations of a material. It's called BCS theory. That is well understood, but that's not going to get us to superconductivity at room temperature anytime soon, or in any realistic system under ambient conditions. Okay, so there's been a real search for sort of unconventional superconductors, right? And one of the very most exciting classes of materials for unconventional superconductivity are a group of oxides, copper oxides, the cuprates, which were discovered in like the 70s and 80s and have still the highest temperatures at which they become superconducting, right? But we still don't understand the mechanism by which that happens. Going back to these 2-dimensional materials I talked about, right, with graphene as one example, usually electrons in graphene do not interact with each other at all. They don't really see each other, and so that's why they're able to, as I said, move without scattering, move, as if they have no mass. Very interesting thing happens when you take 2 layers of graphene and you stack them with a twist. So you just take 2 layers of these carbon atoms, you stack them with some rotational offset, and you create this Moiré superlattice, which is simply this modulation in how the atoms are arranged on each other locally. And in 2018, a group at MIT discovered that when they created these twisted layers and cooled them down to really low temperatures, to be fair, but they superconducted. But what was interesting was that the density that they needed to get the superconductivity to happen was extraordinarily low. You needed very effectively, you could think you needed very, very few electrons for them to interact still extremely strongly, leading to superconductivity. And so this was an amazing discovery that really caused the field to kind of go crazy and has launched an entire sort of subfield in condensed matter physics. One of the questions that was outstanding at the time we started working, my group started in 2018, was what the structure of this material is. So I showed, this cartoon with the twisting and so on, that sort of animation over here. And what we wanted to know is this structure realistic? Is that the real structure of this superconducting material? So the experiment we did is we used electron microscopy. So we have an electron beam that we focus, we pass it through the material. And traditionally, what you would do in electron microscopy or in any microscopy experiment is you ask, for this beam that is going through my material, how much of it is absorbed and how much of it goes through, right? What we did instead is a sort of called a dark field experiment, where we're asking, well, how much of that beam is scattered? Specifically, how much of it is diffracted? And then we take those diffracted beams from each layer. Each layer is going to sort of nudge the beam a little bit. Each layer will nudge the beam a little bit, and then that's going to give rise to a diffraction pattern. And you don't need to know all the details here, but just to say that what we end up doing is we find that if we look at how the beams from each, that are nudged by each of those layers, how they interfere with each other. Remember, an electron is a wave, right? We know that from 1927 or so. So they can interfere constructively or destructively. And if we take that information and process it in various ways, we can actually map the structure of these Moiré superlattices at different angles, right? We can make samples with different angles and we can map the structure. And when we do that, we find, whoa, this observed structure is very, very different from this cartoon that everybody was using with these rigid things. Something has gone on that has actually caused some of those regions where the atoms are right on top of each other to shrink in size and the other regions to expand. All right? And so without going into too much of the details, what we learned from this is actually this is called a band structure. It basically tells you what are the allowed energy levels that electrons in the system can occupy. Every crystal is going to have some basically rules that the electrons in the system have to obey, which dictates the energies that those electrons can have. And in this electronic band structure over here, without any, if you assumed that the cartoon was real, this is what you would get. And it would puzzle you, if you were a theorist, to understand how this system superconducts. In particular, it's a subtle difference, but it's an important one. This flat region over here is touching these sort of more bendy regions. Without getting into details, what you see is that with what we discovered with our model, there is a gap above and below, right? And that makes a world of difference. And so that helped us to understand a little bit more about what allows these systems to display superconductivity. We have also looked at tri-layers. So now you have 3 layers that you can twist and mix and match in various ways. And it gets even more complicated and more interesting. And this electron microscopy tool that we developed allows us to be able to see these materials. Okay. The other thing we ended up doing was to ask, well, what can we do, not in the world of condensed matter physics, but in chemistry with some of these materials that allow us to control how electrons are behaving. And then this goes back to this cartoon of sort of some renewable energy future potential, that we might dream of, maybe one day. Turns out that the dirty little secret in all of surface chemistry is that actually a lot of the time, the stuff that does the chemistry on surfaces in a fuel cell, in an electrolyzer, in your catalytic converter, whatever it might be, are the defects, are areas where the crystal surface is interrupted. There are defects that do also very nice quantum phenomena and sort of single photon emission, but it's the defects that end up doing the heavy lifting to rearrange chemical bonds at those surfaces. But defects are really difficult to control. It's easy to draw a perfect structure. It's very difficult to get a perfect structure. But what is maybe more difficult than that is to say, okay, I'm going to have an imperfect structure exactly the way I want it. And so what we discovered is that actually, by twisting these layers, the same kind of effect that at very low temperatures leads to superconductivity can be used to create effectively tunable defects, so that where the electrons like to sit in these twisted structures can be controlled by twist, whereas they usually are controlled or ill-controlled by defects on regular surfaces. And so we did an experiment where we basically kind of did like your battery or fuel cell or electrolyzer type of experiment. We're passing electricity across some interface of a solid and a liquid, and we're looking at how that electricity is converting into chemical energy, right, at that interface, like a redox reaction. And so we use another nanoscale probe, another new tool called scanning electrochemical cell microscopy, to measure how these twist sort of control impact electrochemistry. And to cut to the chase, what we see is that we can control the rate at which the chemistry is taking place by controlling the angle between these graphene layers, right? Simply, you take the same material and you just twist it, and at different angles, it behaves chemically, in terms of interfacial chemistry, completely differently, right? At one angle versus another. Okay. All right, in the last 2 minutes, I want to give you one last vignette of some of what we do in the area of spintronics. So our conventional computers, as we heard, rely basically on some bit, right? A 0 and a 1 that, as was explained, it is telling us about, well, can we flow charge current, right, through an object, or can we not? In one state of our silicon-based transistors, we are not allowing current to flow, and in another state, we are allowing current to flow. Those are the 0s and the 1s. So that relies on the charge degree of freedom of the electron. The electron has another property, its spin, which is to say every electron can kind of behave as a little bar magnet, right? And so magnetic materials ultimately take advantage of this quantum mechanical property called spin. And so one of the things that is sort of the community is really interested in is thinking about how one can design electronic systems that, instead of relying on the charge of the electron, leverage its spin, either exclusively or in addition to charge, right? As a way of pushing the frontier of electronic systems performance and power efficiency. Okay, so we take two-dimensional materials, and the way we design some really interesting magnetic crystals is by now, I would like to say that we're kind of like trapping atoms. That would be very, very cool. But we're putting them between the layers of some other crystal, right? So we're taking some atom that has spin, has unpaired spins, and we're going to put it between the layers of some other crystal, and that looks something like this. So that our crystals look like so, where we have sort of the more continuous dots are the main crystal originally, and then we put other magnetic ions in between, and by controlling the spacing between these so-called intercalated ions, we can control the magnetism of the system. I'll give you an example. Here what you're looking at is a material where the spins form a helix. And what we're doing here, if you follow closely, as a function of magnetic field in the electron microscope, we are watching how those spins reconfigure. As we apply more and more magnetic field, we take that helix and we unwind it continuously. So you see these horizontal lines. We unwind them until at some point they vanish completely. And so this is a way of effectively storing information in how many coils, how many windings there are in the magnetic material. And the reason this is important, this is my last slide, is that this family of materials, a collaborator of mine, James Nalidis, also at Berkeley in the physics department, we're working together because we've found that there is one of these materials, the same type of structure I showed you before, it turns out it allows extraordinarily low switching between two states. Typically, when you want to switch the magnetic properties of a material, you need about 1 million amps per square centimeter in basically all conventional magnetic systems. These materials that I've shown you, they require 2 orders of magnitude lower current to switch. And so and it's very sharp and very reproducible. And so we're trying to understand, one, where does this come from? What's the origin of this, and how can we leverage that moving forward? Okay, so I hope I've shown you 3 things about our work using electron microscopy to image superconducting materials, to tailor chemistry at surfaces, and also to design magnetic, so-called spintronic materials that lead to this really low power, low energy cost switching between various states. So again, I'm thankful to my group for their hard work on this, and I'm thankful to you for your attention and to the organizers in the first place for the invitation. Happy to take any questions.